Half-lives are due to the random nature of radioactive decay, and half-life is the time taken for the activity or the count to half. So for example, if we start off with a sample that's giving off 200 becquerels, after the first half-life, so I'll put 1 and a circle around it, so after the first half-life we have 100 becquerels. After the second half-life we would have 50 becquerels, and after the third half-life we would have 25 becquerels, and this number gets smaller and smaller and smaller, approaching 0 but never actually gets to 0. So for example, if each half-life was 5 minutes, half-life is constant, so that's 5 mins, that's 5 mins, that's 5 mins. It's taken a total of 5, 10, 15 minutes to go from 200 to 25 becquerels. Half-lives can be measured in seconds, days, weeks, years, or even millennium for some slowly decaying unstable isotopes. We can also represent it not just as numbers but as percentages. So for example, if you start off with 100% after one half-life, you've got 50%. After a second half-life, you've got 25%. After the third half-life, you've got 12.5%. Further still, you can represent it as a fraction. So 1 over 1 equals 1. So we start off with a whole. After one half-life, we've got a half. After a second half-life, we've got a quarter. After a third half-life, we've got an eighth. And again, this goes on and on and on. For higher tier only, you need to be able to represent it as a ratio. So 1 is just 1. After one half-life, you've got 1 to 2. After a second half-life, you've got 1 to 4. And after a third half-life, you've got 1 to 8. So that's for higher tier only. We can also represent half-life on graphs. So for here, we've got a graph that the count rate is started at 1,000 and it's decreased over time. So let's label that up, count rate. That can be count rate per second. And on the x-axis, we've got time. And again, that could be seconds, days, minutes, hours, weeks, years, decades, millennium. Doesn't really matter. What does matter is how we do it. We look at where the graph meets the y-axis, and it's meeting there at 1,000. We half 1,000, so 1,000 divided by 2 equals 500. We go to our y-axis 500 and we draw a line across straight using a ruler. I'm showing a bad example by not using a ruler. Once we hit our graph, we then draw a line down again using our ruler, and that tells us the half-life. So my half-life in this case equals 2.5, whatever the units is. So for example, if the time's in days, my half-life is 2.5 days. So that's how we find a half-life from a graph. When you're doing these half-lives here, this is working from the starting amount to the end. You could be told the final amount. For example, let's say you're given a final amount of 10 grams, given a final amount of 10 grams, and you're asked to find out how many half-lives or how long it takes to get to 40 grams. So one half-life gets us to 20 grams, a second half-life would get us to 40 grams. And if they told us that took 20 days, so 20 days equals 2 half-lives. Each half-life must be 10 days. And that is radioactive decay in terms of half-lives.